So I think we should be officially live now with everyone. Is there a view, Nikolai, where I can see the participants? Okay, this is where I see it. So, so welcome everybody to an afternoon together with Force Technology and GlycoSpot. I am Jonas Jacobsen, and I'm heading up our commercial activities here at GlycoSpot. And I've been given the honor to introduce the webinar this afternoon. We have given it the title, How to Control Enzyme Performance in Your CIP Process. And I think that that very well gives us a frame for the objective of the webinar this afternoon. The use of enzymes in CIP processes is, as you probably know, an effective way to improve sustainability. And enzymes can sometimes be a part of solutions, sometimes they are not. But when they are part of the solutions, it's valuable to understand how they function when they are most active, when they're in the optimum, and definitely also when they are not a part of the process any longer. So when do you have a so to say a cleaner rinse water after you have completed your CIP? So I think we are truly privileged this afternoon to have Annette Balser Larsen from Force with us, and our own senior scientist Brian King. And I think first of all we'll have Annette take stage and give us an introduction to the basic principles of CIP processes. And following up on Annette's presentation, Brian will try to put it into the context of enzymes and how measurements of enzymes both during process and also in the rinse water in the wash can be a valuable tool in optimizing CIP processes. So that's my introduction, and with that I'll leave the word to you, Annette. Thank you.
Thank you. And I will share my screen. And hopefully you can see it now. Can you see my screen?
Yes.
Perfect. So thank you for the opportunity to talk about these topics. It is very important to have an optimized cleaning process and to have the cleaning validation after that. First, I will start very shortly to tell about very shortly about Force Technology, then a little about myself, and then we are coming to the agenda for my speech. So what is Force Technology? We are an independent, self-governing institution, and we have consultancy and testing facilities. We are also one of the 7 GTS Institute in Denmark. And as a GTS Institute, we are dedicated to develop and apply the technologies and new knowledge for the benefit of the business world and society as a whole. I decide not to talk about what Force can beside these topics, but if you need to see, if you have to see it, then you can go to the website here. Very shortly about the key figures. This is from 2020. We have a turnover of 1.1 billion, and almost half of this turnover is from abroad. This is customers from international companies. We are 1,100 employees. We have more than 8,000 customers worldwide. We have more than 400 unique facilities. It is lab facilities, it is test facilities. Under normal conditions, we have a very large course palette. So we have more than 5,000 course participants worldwide. And we have more than 150 collaboration projects, 35 new R&D projects, and we have more than 50 different disciplines, where the hygiene, cleaning optimization is one of them. So very shortly about myself, I'm Annette Balser from Force Technology. I'm a senior consultant. I'm educated dairy engineer. I have the last 24 24 years, I have worked with food safety, product quality, hygiene, cleaning validation, hygienic design, and biofilm, and the last 13 years at Force Technology. I'm going to talk a little about biofilm very shortly, because it's very important to know which challenges the biofilm can make for us in the equipment. Then I'm going to the cleaning process, the CIP, or cleaning in place, with both the chemical agents and the enzyme step. And in the speech, I have 2 cases. But first, about the biofilm. Well, we know that in every production where there are a little amount of water, the biofilm formation will go on. So it is very important when we have the cleaning step that this cleaning step are going to remove all the formed biofilm during the production time. A small example, because we cannot understand totally the biofilm formation, but we know when we have our teeth and we brush our teeth, if it's not good enough, we can feel a little roughness on the surface of our teeth. You can't see this roughness. Here you can see it, but it's because it's very heavy. But normally you can't see it, but you can feel it. This biofilm formation, or plaque we are talking about when we're talking about the teeth, this biofilm formation, we can get it on the stainless steel too. Here we have biofilm formation on a stainless steel surface. This biofilm formation will give contamination to the product flow that is across this surface. Maybe this contamination will give quality problems, maybe even food safety problems. This biofilm formation, you can't see it, but it will contaminate. And the last picture here, we have an agitator. This specific case with this agitator, there was not used hygienic design. Hygienic design is very important to get the effective cleaning. In this specific case, we have a bend right here. Because of this bend, the cleaning water from the CIP nozzle here can reach this side of the bend of the agitator, but it can reach the other side. So this side are not going to be clean, and are we looking on the other side here on the agitator? This CIP nozzle are going to clean this side, but not the back side. So we have a not optimized cleaning, and the cleaning validation is not good. What is the challenge? Well, we have contamination of the product with the microorganisms in this biofilm, but we can also have biocorrosion. And what is biocorrosion? Well, underneath this biofilm, we can get the biocorrosion, which is like the picture here. The stainless steel is the white here, and biocorrosion or corrosion of stainless steel give pits. We have the surface to the product side here, and when the pits are going to grow, they start with a little pinpoint here and growing down in the stainless steel. So we can only imagine, is this easy to clean? And no, it is not. That's why it is so important to clean properly, to get all the biofilm away from the surfaces to avoid these pits. So the cleaning procedure is very important. When we have a look on our washing of our clothes, we are using enzymes and low temperature. We are using the enzymes, they act as boosters, and we can wash our clothes, our laundry with low temperature. When we're looking at the enzymes, we have the enzyme here and we have the substrate, the soil. They complexed to a enzyme substrate complex, and because of the acting of the enzyme can split, degrade, if we can say that, the substrate into two products, and it's easier to clean. So the enzyme, they are for a specific task. We are call it key to lock principle. And after releasing the products here, we can get the enzyme can be used again. So the enzymes are designed to degrade proteins, that is proteinases, starch, that is amylases, and fat, that is lipases. So at low temperature, we can wash the clothes effectively and good. When we are looking at the cleaning procedure in general in the industry, then we have this sinuous circle. We are talking here about the CIP, or cleaning in place. That is cleaning of the closed system, pipes, tanks, and so on. So when we have these four parameters, we have to optimize these. So is the agent maybe a little bit smaller here? The other parts have to be bigger to fill out the circle. The most difficult part to get optimized is the mechanical effect, because it's depend in very high degree of the hygienic design. It is very important in both the ordinary CIP cleaning and in the enzyme step cleaning, which also could be in the CIP in the closed system. If we are talking about the flow rate in the pipes, we should have it between 1.5 to 2.5 meter per second. That gives the turbulent flow, and that is the optimal flow for the optimal cleaning. When we are looking, I'm not going to read this up because we're going further. The next slide is for the membranes, and that is much more relevant for us in this case. But the mechanical effect is very, very important. Here we have an example of the mechanical effect, or it is a pipe with a welt that is swollen. You can see the welt here. It is swollen, and we have the flow here, and then we can think that on the opposite side, also on this side of the welt, but also here on the opposite side of the welt, the flow is different. It is much lower, maybe 0 meter per second right here. We can also see the light brown right here. It is actually biofilm formation on the opposite side of this welt. Not mixed up with the heat zone here, the darker brown zone, that is a heat zone because of a bad welding. The heat zone, it has been too high in temperature, and the heat zone is less resistant to corrosion. You remember the pits I talked about at the biofilm slide, and all the white spots we have here is actually beginning of pits because of the heating zone, too high temperature when you're going to make the weld. We are going to cleaning in place on membranes. And in this specific case, we have PHT membranes. It is very important to mention that because these membranes can tolerate more than many membranes can. These PHT membranes are for the UF filtration. This company, they have both the ordinary CIP and they have to have an enzyme step 2 Sometimes it's used few times a week, sometimes during the weekend. So always after the production time, they are going to have the ordinary SIP, and a few times a week, and maybe in the weekend, they are going to have the enzyme SIP too. The ordinary SIP is first a rinse, then a cleaning with an alkaline. And here we can see that these membranes can tolerate higher pH than many membranes can tolerate, and higher temperature. The pH is 12 and the temperature is 70. And it's a long time, 35 to 40 minutes. If we compare with the SIP I show you in the last slides, it was only 6 to 15 minutes in the closed system. So this is a long time. Then the rinse, cleaning with the acidic, and rinse at last. And with this cleaning procedure, this is not necessary. It is not enough. It is not enough to get the whole biofilm formation in the membrane to remove this. And what is the temperature, the time, the pH is quite high, but the mechanical effect is the very difficult part when cleaning the membranes. So we have to have the enzyme step. So first, every time we are going to have the ordinary cleaning step with the cleaning agents. And after that, we have the cleaning with the enzyme step. When we're using it a few times a week, we have a pH of 10, temperature of 50, and a time 30 to 40 minutes. When we are using it on the weekend, we are going to have the same solution here, the enzyme step, but we keep the solution in the membrane equipment for the next 48 hours and then rinse it out. Very important after using enzyme step is the inactivation step of the enzymes. So we have to rinse, we have to use, in this case, alkaline, a long time, 30 to 40 minutes, and then a rinse in the end. This step is actually the same step that the first step here in the ordinary SIP cleaning. So the inactivation step for the enzymes is very, very important. We could have high, this case is high pH, but the pH to inactivate can also be a low pH. And together with temperature, it will determine the length of the inactivation step. It is very important always to use the specification from the supplier of the enzyme detergent, and of course the limit for the toleration for the membranes, because many membranes cannot tolerate such a high pH or low pH and high temperature. That gives it more difficult to optimize the cleaning process. So even though that these membranes can tolerate higher pH, higher temperature and lower pH, it is still necessary to have the enzyme step to get the clean membranes. Here we have a case. It is UF membranes that is only cleaned with chemical agents, and we can see it is not good enough. The company have to buy new membranes for the equipment. It was quite expensive, 400,000 or more Danish crowns for this equipment. Besides of this, they have the last month have lower performance of the equipment and higher contamination to the product flow. The sustainability issue in this, using both the chemicals and enzyme step, it is to ensure that the membranes are clean. That gives a better performance of the equipment, lesser contamination to the product flow, and longer shelf life for the membranes. But there are also challenges when using enzymes as detergents in the cleaning process. We talked about it when we have the wash of our laundry, that the enzymes have the specific task, they key to lock principle. So if there are any enzymes left in after cleaning process, in the cleaning process, the enzymes here are going to make a complex with the substrate. The substrate here is organic material. It is a product, biofilm formation in the equipment. So if there are any enzymes left after the cleaning process, they can degrade the product during the shelf life. This means that if we are using enzymes in the cleaning process, it is very important that the detection level of the residue enzymes must be very low in the rinse water. The taste is very often associated with the activity of enzymes during shelf life, or you can see the picture here is cheeses. So in the cheeses context is the maturation of the cheeses. So if you have a higher pool of enzymes in your product flow, you can have another developing of your taste in the product, and you can even destroy it, or it's going to be very badly taste. And the last case is the pasteurizer used for concentrate. It has a production time of 8 hours. It is concentrate that is have a high protein content that gives quicker biofilm formation in the equipment in the pasteurizer, and we can see that the proteins here is burnt on the plates. The cleaning process is an ordinary cleaning in place procedure. It's three-step with rinse, alkaline, and rinse. And you can see it's obviously not good enough. The company choose a enzyme wash, first a rinse, then the enzyme wash, an overnight wash, then a rinse again, and an inactivation step. And because of this pasteurizer is made of stainless steel, they can use high in the temperature and high in pH. After the enzyme wash, they analyzed the last rinse water after cleaning. It was not for activity of the enzymes, but more the effectiveness of the enzyme wash versus the cleaning with the chemical detergents. And here's the results. We are analyzing the last rinse water after the enzyme wash here, and we can see on the petri dish only 3 colonies grow on the petri dish. Then we have an ordinary production with the pasteurizer, 8 hours. We have the ordinary cleaning process, and then the last rinse water again, and we can see on the petri dish 65 colony are grown. So the conclusion here is that the ordinary cleaning process is not good enough. It is not possible to make the cleaning sufficient and optimal. So they have to use the enzyme wash too. A conclusion: some equipment used in the industry are difficult to clean properly with the ordinary cleaning process. We have to remember that hygienic design is very important to optimize the mechanical effect. Enzyme cleaning can be a good and sometimes extra step to the ordinary cleaning process. In both cases, the cleaning was not good enough. If we look at case 1, the membranes, it is very difficult to get the appropriate mechanical effect inside the membranes. The other parameters we have here in the center circle have to be higher to fulfill the circle. And then there are some problems when using membranes because they can very often not tolerate high or low pH and high temperature. And in the specific case with a PHT membrane, they can tolerate higher pH, higher temperature. But anyway, it was necessary to have the enzyme step. At case 2, we have the pasteurizer with the concentrate. We have burn of proteins and biofilm formation. And again, we have to look at the center circle. Is it possible to optimize the parameters even more? And in this case, it was not possible. So we have to use the enzyme cleaning. When we are using the ordinary cleaning process, we have to make sure that the chemical detergents are flushed out after the production of the production line before the next production start. And using the enzyme step, it is very, very important that we have the effective inactivation step to ensure that there is no or only minimal amount of enzymes left in the equipment to the next production. So the sustainable issue, the enzymes can degrade soil or biofilm burn of the proteins that is very difficult to remove from the surfaces. That gives better cleanability of the equipment that is difficult to clean properly and longer shelf life for the equipment. So home methods, it is very important which conditions the equipment, for example, membranes can tolerate. Use always the specification that is given for the enzyme detergents for the supplier and the above toleration of the equipment here. And remember an efficient inactivity of the enzymes after use before the next production. If too many active enzymes left, it can destroy or degrade the product. It will depend on the product, the shelf life, the pool of enzymes in the product now, the pool of enzymes from the non-starter in the product, and so on. Thank you.
Thanks a lot, Annette. I think some very interesting use cases on the applicability and importance of enzymes. So interesting to hear. I think I forgot to mention that in the right pane of your webinar here, you have the ability to, or the possibility to ask questions. I can see so far one question is in for Annette. We're gonna group the questions and hit Brian and Annette with the questions after Brian is giving his session. So I think with that, I'll leave the stage to you, Brian, to enlighten us on the, let's say, the powerful tools that we can offer here at GlycoSpot as a way of understanding enzymes in the processes, CIP processes even better.
All right, thank you, Jonas, and thank you, Annette. I will just share my presentation here. Yes, and I assume that you can see this. But yeah, so yes, thank you, and thank you again, Annette, for presenting a nice introduction to CIP processes and why enzyme treatments can be of a special interest when there's heavy residue or biofilms or poor flow dynamics. So to start with, I will give a brief introduction to who our company is. So we are a biotechnology company and a device company outside of Copenhagen, Denmark. We were founded in 2014 and currently have 16 employees. And our mission is it's based around enzyme assays. So we innovate and bring to market application-specific enzyme tests methods that are fast to implement and easy to use. So I think that's a key point of what we strive to do at GlycoSpot, is to make simple methods that are fast to perform, so in the matter of minutes to perform, and easy to implement into your existing processes. We have a variety of different products that we offer, but our primary focuses are on the malt and brewing industries, as well as CIP cleaning. which will be the focus of what I'm talking about today. So again, it's clear why enzymes could be useful and why it's interesting to be using enzymes in a CIP process. It helps remove these plaques and residues, and especially in very difficult to clean systems. However, why not, or why is it interesting to measure enzyme activity? And so I think part of the challenge is that it's a bit of a black box. So it's a bit unclear sometimes how enzymes are working or what the optimal parameters of the enzymes are. But there are a lot of interesting places that it could be used. So you could measure your enzyme activity while you're evaluating different products from different companies, for example. So there's a range of proteases and lipases and other enzymes that can be used to clean in CIP. And then there's also all the non-enzymatic components of the cleaning, so all the detergents and surfactants and alkaline and acidic chemistry. So by measuring enzyme activity and how it interacts with all these different products, as well as your particular process, it can help you choose the right product for your use case. Additionally, when you, as a company that's producing food, for example, when you take in your chemicals, perhaps they sit in storage for a number of months before that product is fully used up. And especially because enzymes are a biological product, they do have a finite shelf life, and so their activity can decrease over time. So by periodically measuring your stocks of chemicals containing enzymes, it's possible to see when a particular batch of product is out of date, or the activity is too low and it's time to order a new fresh batch of chemicals. Additionally, you can, by measuring enzyme activity, you can have an extra level of quality control in your process and consistency in your process, so that you know that every time you're running your process, you're getting the same performance as you would expect, and that there's not something wrong, or that a small mistake was made, or whatever, things are out of spec. So it's a way of monitoring your process and ensuring consistency in your cleaning process. Additionally, it could be used to optimize your cleaning. So by changing these parameters, which I'll get into in a little bit, by changing the parameters of the cleaning, you can potentially improve your process. So to either reduce the usage of chemicals, reduce the amount of energy that you're using to heat the system, reduce the amount of water that you're using to rinse the system, and generally optimize your process both for improved performance, to save time, to save energy, and in the end, save money. It also, as was mentioned several times, is important to ensure that the final rinse has been fully, the enzymes have been fully inactivated and also rinsed away. So, because if there are dead spaces or hidden pockets of residual cleaning solution that contain enzymes, or if for whatever reason the enzymes were not fully inactivated, then that can contaminate the next batch of production, say if you're making cheese, which will influence and have a negative impact on the quality of the product. And finally, there may be compliance reasons to be measuring enzyme activity. So either for standards that have been set within your company, or also regulations for wastewater disposal, or for example, if you're in food processing, to demonstrate that there are no residual processing aids in your product. So as I mentioned, there are a number of places where it's interesting to test your enzymatic activity. And so the first place, as I mentioned, is before the product has even entered into your system. So It can help to, again, evaluate different competitors' products. It can ensure that the batch of the material that you're getting is consistent and meets the specifications of the product. And also, as your material has been stored, that the quality is still acceptable to be using in your cleaning process. So this is measuring the activity of your enzymes before it ever enters the cleaning system. But then once it enters the cleaning system, it's possible to either take samples potentially during the cleaning process, or simulate the cleaning process separately from the tank itself. And so this allows you to evaluate all the different parameters in the cleaning process to make sure that your enzymes are performing as well as they can. The third place where it could be interesting to be measuring enzyme activity is also then again in this rinse, or at the end of the cleaning process. So in this case, the enzymes should have been inactivated either through high temperature or high or low pH, as well as just dilution effects from rinsing. But again, things can go wrong. There can be hidden spaces, and it's possible to have residues from your enzymes carry over when you think your tank is clean, but in reality, there's still trace amounts of enzyme activity that could damage future production. And then a fourth case, which may be interesting if you are recycling your CIP solutions. So in the case of cleaning a very heavily contaminated or a very dirty system, maybe the cleaning solution is too dirty to recycle. But if you're just doing routine cleaning and it's a relatively light cleaning, it may be interesting to save the cleaning solution and recycle it. However, again, because enzymes are biological, they do degrade over time, and so it may be necessary to add more protease or lipase or whatever enzyme you're using to introduce it back into the tank and then increase the concentration of the enzymes. And then there may be other cases where it will be interesting to measure as well. So if you are using enzymes in your cleaning process and you have a particular use case, we of course would be happy to hear about how we could help you. But so we've established that it's interesting to use enzymes. It may be interesting to measure enzymes, but the challenge is still that enzymes can be difficult to work with. So even in a perfect laboratory environment, there are many factors that influence the activity and stability of enzymes. And then when you move into a field situation or a real production situation, the complexity becomes even more great. So for example, there are a number of factors that can influence the activity and stability of enzymes. So for example, time. As has been mentioned several times, the enzyme activity will decrease over time, especially in the case of elevated temperatures or extreme chemical situations, like, for example, caustics or detergents. Additionally, if you are doing a long cleaning process with enzymes, say a soak over the weekend for 48 hours, the activity of your enzymes when you start that process will be greater than the activity of the enzymes at the end of the process. So it may be interesting, even if you're doing a soaking process, perhaps to top up the enzyme concentration over the process of a long cleaning to get the most enzymatic power. Temperature has a strong effect on the activity of enzymes. However, if you go too high in temperature, then that also will severely reduce the time at which the enzymes are active, or they will degrade more quickly. So temperature is important to balance the enzyme, the optimum temperatures for the enzymes with the duration of the process. In the case of pH, many of the, if we're talking about proteases, for cleaning purposes, they typically have a pH optimum that is alkaline, so around, say, pH of 10. So having the appropriate amount of caustic chemical to add to your solution, to your cleaning solutions, especially in the case of a heavy residue, which may require more caustic to bring the pH up. It's important to be able to measure the pH and how that impacts the activity of your enzymes. And then also with detergents and surfactants are useful for breaking up these residues and cleaning stainless steel. However, these same detergents and surfactants, especially when combined with these other parameters, also will denature proteins potentially and reduce the effective activity. The amount of soil and the type of soil can have an impact. So if you have a soil that has a lot of heavy protein or heavy lipid amount in the soil, that can also have an interaction with how the enzymes are behaving. And then finally, with water hardness, if you are rinsing, so for example, certain ions like calcium can have a strong impact on how active enzymes are, for example, proteases. And so if you're rinsing with distilled water or municipal water, the amount of calcium in your system can also have a significant impact on how active your enzymes are. So at GlycoSpot, as was mentioned, we have put a lot of work into making our assays as simple to operate as possible. So it's a simple assay where we can provide a special substrate prepared in individual reaction tubes. So all that's required by the user is to add a sample for example, from a cleaning process. Then you incubate your sample, which contains the enzymes. You incubate the sample for 5 minutes, and then you measure in our specially designed spectrophotometer, which is a small device that connects over Bluetooth and gives a result on your phone. So it's a lab-free solution that can be used on the production floor. To give an example of how this assay can be used to evaluate and optimize cleaning processes, this is some data that was generated that shows the effect of enzyme concentration on the left here, the effect of pH in the middle, and then the effect of temperature on the right. And so this was an experiment that was performed in our laboratory where we designed a set of conditions to cover all the different space of these three parameters within the boundaries that we set. So what is shown on the y-axis here is enzyme activity, which is measured by our colorimetric readout from the enzyme assay measured on the spectrophotometer. So if you look at, to start with on the left here, with the enzyme detergent concentration. So this is a detergent which contains protease. And so with the increasing amount of detergent, we have increasing amount of enzyme activity, which is to be expected. And it's a linear dose response. So if you want more enzyme activity, then you can just add more of your enzyme detergent. In this center part here, this is showing the dose of a alkali chemical to bring the pH up to 9.5 or 10 with the higher dosage here. And so this will depend on the amount of soil in your system, for example. but also you can see that with the increasing dosage of the alkaline reagent or the alkaline chemical, which increases the pH up to the optimum pH for the enzymes, we also have a linear increase in the activity of the enzymes. However, what's a bit interesting is that for this particular example, the temperature, so there was an increase in temperature, or the increase in enzyme activity moving from, say, 30 degrees up to 40 degrees. However, when the assay was moved from 40 degrees to 50 degrees, there was no further increase in the strength of the enzymatic activity. And so in this sense, it could be potentially you could save energy by running the reactions at a lower temperature, say below 40 degrees. So to explore this in a bit more detail, another experiment was done in a similar case. So in this example, the concentration of the enzyme was kept constant. So all of these, and it's still showing the enzyme activity here on the y-axis. And then what was adjusted was, again, the amount of alkali that was added. And this is an independent experiment from the previous data that I showed, but with the same concentrations. So on the left here is a low dosage of alkali product, in the middle is a moderate dosage, and then on the right is a high dosage of alkali product, which increased the pH from the starting pH of 7.5 with a low dosage of the alkali chemical, increasing to 8.5 or up to 9.5, which is closer to the optimum for the protease. And then the three bars in the three different colors are showing the different temperatures. So at 30 degrees, 40 degrees, and 50 degrees. And at the low dosage of alkali, which is quite a ways away, so it's still within the window of activity of the protease. However, it's a bit below what the optimum is. We have relatively low activity, but there's a clear increase in activity with higher temperatures. However, at the moderate and high dosages of the alkali, you can see that there's a large increase, almost a double increase in the activity, going from a 30-degree process to a 40-degree process. But then there's no difference in activity between 40 degrees and 50 degrees. So again, just to emphasize that all of this activity, this range of activity, there's close to a 10-fold range of activity that you can get just by changing the temperature and the pH of the system. And it should be mentioned that this is just one example. So I'm not recommending that everybody change their processes from 50 degrees to 40 degrees. However, this is just an example, though, where it would be worthwhile to investigate whether the energy savings that you get by reducing the temperature is if that outweighs the or if that balances with the enzymatic activity and the additional benefits that you would get from a higher temperature process with the removal of residues from just the chemicals. So it's a complicated system where you have to balance a lot of different things like temperature, pH, enzyme activity, mechanical flow, and all the things that Annette was discussing in the first part of this webinar. We have tested our assay with a number of proteases. This is just highlighting a few of the most common or some of the commonly used proteases for CIP cleaning. And so, it shows the limits of detection using our assay. So these are the limits of detection with only making a single measurement in rinse water, for example. To validate that there has been inactivation and removal of the enzymes. And these limits of detection could be even lower if you make multiple measurements but even a single measurement should give you a good estimation of how much activity you have, even down in low concentrations. So again, this is in the parts per billion of protease products. So to conclude, these are just some images of the product. And so again, we package our substrates into these single-use tubes, and we supply the reaction buffer and stopping reagents. If you need a incubator or a carrying case, we can supply those. And then our Sirius spectrophotometer, which connects over Bluetooth to your mobile phone or tablet. And yeah, all of these together allow for on-site evaluation of enzymatic activity in your cleaning process. So if you're interested in more information, you're of course welcome to contact me or anybody else from our company. We're happy to discuss more. So with that, I think that is it for me. So thank you.
Thank you, Brian. So great presentations and presenting some of the the trickiness of enzymes when you work with them. I think you framed it quite well. We have a number of questions coming in. First question, I think, would probably be you, Annette, that could help us answering that. It's on the sewage sludge. So when using cleaning enzymes in CIP solutions, can it be problematic that they're still active in the sewage, and how do you ensure the correct sewage treatment?
It could be. It depends on the content in the sewage and so on. So it could be. So you have to have as low as possible the content of the enzymes in the rinse water. Yeah.
And then we have another question, which I think is spot on for you, Brian. It almost sounds like a GlycoSpot question, but in fact it's not. So the question is, what is the most effective way of measuring the amount of enzymes in residual water?
Well, I would say it's using our assay, but so the most effective way of measuring enzymes in the rinse water. So yeah, so using our assay, which is a highly sensitive substrate, it's possible to detect these very low quantities of enzyme activity. And our standard assay, it takes 5 minutes, is a 5-minute reaction time. But by increasing the time of the reaction, you can also increase the sensitivity. So there are a number of tricks you can do to get even lower levels of sensitivity. And yeah, so it's just a matter of taking a sample of the rinse water and periodically measuring it, either using a short 5-minute assay, or if you have the time, you can let it run for even up to an hour, which will increase the signal even more. But yeah, that would be my suggestion.
Thanks, Brian. And I think that actually answers one of the other questions we have in, which is how much time does the test take? And I think we have a standard let's say test protocol, which is 15 minutes. But if you want to play with the sensitivity, of course, prolonged incubation is a way of getting higher signals, or getting signals in that are above a detection limit of the assay. So you mentioned even up to 60 minutes if you really want to push the limits here, or maybe even longer. So, but in principle, the assay as such is fast to conduct, and there are different parameters you can play with if what you're targeting is extremely high sensitivity.
Yeah, and just to follow up on the time of the assay, so it's 15 minutes from the start of from adding your sample until you have the result on your phone. Yeah. And you can also stagger multiple measurements over that period. So if you're very efficient in how you're doing it, you can measure 10 or more samples over half an hour or something like that.
Yeah. There is another question here, and that is probably also for you, Brian. And it goes, does the assay work with all protease products?
It has worked with all the products that we have tested. So it's worked with these commercial products that I showed on the slide. So alkylase, savinase, and we've also tested it on other non-CIP protease products as well, which is also worked. So I think for CIP cleaning, most of these enzymes are quite general in their substrate specificities. So it's worked for what we've tested it for, but we're happy to test new enzymes if somebody has something that they particularly are interested in.
Yeah. So I think basically what you're saying, Brian, is that if we can, tick it off on our list of enzymes we've already tested, the test kit is sort of good to go. If it's other enzymes that we have not played around with yet or validated the assay on yet, we would do a minor validation internally and confirm the usability of that particular test kit for that protease.
Yeah.
And another, and that's probably the second last question here, at least so far, and that goes on enzymes beyond proteases. Is it possible to measure activity of other enzymes, for instance, lipases?
Yes. Yeah. Yes. So you can measure lipase as well. Yeah, we have experience working with lipases, as well as amylases and carbohydrate active enzymes. I think GlycoSpot originally was working a lot with carbohydrate active enzymes and still is, especially as I mentioned at the beginning with the malt and brewing segments. But we have assays when we have a range of substrates as well for amylases and other types of enzymes that could be interesting for both CIP, but as well as detergents and laundry and food processing, lots of different applications. Uh-oh, I think we've lost Jonas, and he's back.
It's gone again.
We are back again now. Yeah, we just had a fallout on the connection.
Yes, but I think I've answered the question. And if somebody is really interested,
we could hear your answer, Brian. It was just our connection that fell out our footage.
Yeah, but we have a list on our website of all of our custom substrates that we can work with.
Yeah. Another question, or maybe the last question for now: what level of proteolytic activity can be considered a risk for following production batches? I think that's actually a pretty difficult question to answer, at least with the when I think about my background working with enzymes in production plants in food processing. It's I don't know if you have any comments, Annette or Brian, but I think my answer would be that indeed depends very much on the particular finished product or food. You mentioned cheeses, and it could be other food products, and the particular specific activity of the enzyme and how that potentially conflicts with the quality of the food product. So I think that would be very empirical to answer.
Yeah, it is very difficult to answer because it's dependent on the product. It depends of the pool of enzymes in the product. If we have to consider for and against enzyme, not enzyme in the cleaning process. So if we are not using enzyme in the cleaning process, we can have a not cleaned membrane. And what difficulties does that give to the production? How many non-starter enzymes are coming to the production by the contamination of this not clean equipment? So it depends on a lot of things.
Very good.
Yeah, I can just have one comment. So we have one example that we were working with where, for example, if an active cleaning dose of a particular protease was 2,000 parts per million, we were able to demonstrate down to all right, now my math is going to get me in trouble off the top of my head, but down to 5 parts per million or something like, or 10 parts per million. And so we were able to demonstrate 99.95% removal of enzymes, and for this particular case, that was sufficient.
All right, Brian and Annette and our group of participants today. I think that concludes with 60 minutes of intense webinar and a bunch of good questions and some and even some difficult ones amongst. Thank you very much to all of you. We are going to have, if you want to learn more about GlycoSpot products or how you can collaborate with GlycoSpot, we're gonna share a link soon after we conclude today, and we are going to follow up with an email. And if you cannot wait, you're welcome to contact us directly, as Brian mentioned. So, thanks a lot.
Yeah, thank you.
Thank you.
Yeah.